Morning everyone. This video is for students of Advanced Higher Graphic Communications looking at simulations, in particular finite element analysis and computational flow dynamics. If you've come here and you're looking for an in-depth explanation of what finite element analysis is and computational flow dynamics, then you've probably come to the wrong place. This is only really designed for those pupils doing Advanced Higher Graphics in Scottish education. So apologies if you're looking for something a bit more complex and detailed, this probably isn't the place for you. Those of us who are still here, we're going to have a look at the Channel Tunnel, which joins Britain with the European continent. And it's a rail tunnel, and our intention today is to have a look at the finite element analysis and the computational flow dynamics that may have been done prior to that tunnel being constructed. This is not an historically accurate video, it's simply a thought about the kind of simulations that would have been done. So let's get started. The Channel Tunnel itself is just over 50 kilometres long, and it consists of two main tunnels which are 7.6 metres in diameter. One tunnel goes from the British side to the French side, and the other tunnel goes in the opposite direction. So it's a kind of one-way system. And in between the two of those tunnels there is a slightly smaller diameter tunnel of 4.6 metres, which is for maintenance and also for safety and evacuation when it comes to emergencies. And we'll come back to that nearer the end of this video. So three main tunnels. The walls of the tunnels, after they've been bored by the tunnel boring machine, are then lined with concrete segments. And when you bolt these concrete segments together, they form this circular tunnel wall. And they're there to resist the pressures of the water and the soil which is above it. Inside the tunnel, when the train is going through, it's got a maximum speed of 160 kilometers an hour, which is just slightly short of 100 miles per hour. With all of that in mind, what simulations would the designers have to consider? Remember, this is not what actually happened, it's just my view of what could have happened. Looking at finite element analysis to begin with, we can see here a photograph of the tunnel itself. Round the outside you can see the concrete segments, and you can see the holes where the bolts attach them to the surrounding soil. When you put these segments together, they form a perfect circle. And I think there's about 9 or 10 segments which are joined together to create that full circle. And this is the way that an awful lot of tunnels are created. The boring machine goes through, and as the machine passes, it then lines the tunnel automatically with these segments. So it's a fairly conventional approach. However, when designing the size, thickness, and how they're attached to the wall itself, the engineer would have to do some kind of finite element analysis. And we've got here a little indication. It's not the Channel Tunnel, but it's something similar. And we can see from the colours used in that simulation where we think the greatest stress is going to be. As expected in this one, it's at the very top wall of the tunnel. So the engineers, when deciding the number and thickness and attachment method for the segments, would have to consider all of these different pressures. Another finite element analysis which might have been done is on the track itself. The track's not perfectly straight going through the tunnel, it does curve ever so slightly from left to right, and when it's doing that, the train will exert some pressure on the side of the rails. You've probably felt that in a train. When it's going round a corner, you'll feel yourself thrown a little bit to one side or the other. And what the engineers have to do is make sure that the rail and the sleepers that the rail is attached to are sufficiently strong to resist that pressure. We don't want the rails moving. We want them staying in place. So there would be some finite element analysis simulation done to make sure that all the parts of that track system are strong enough to withstand that turning pressure. Another analysis that would perhaps be done would be looking at the wheels themselves and how they connect with the track. And this would simply be to make sure that the track is sufficiently strong to withstand the speed and the weight of the train passing through. Remember, some of these trains have got commercial vehicles on them, trucks and buses, which are much heavier than human passengers, So the track has to be strong enough to withstand that weight as well. That's 3 simple finite element analyses which may have been done. There would be lots of other testing and simulation involving signalling and electrical systems, but we've just looked at 3 simple, sort of mechanical, finite element analysis simulations. Let's move on to computational flow dynamics. Remember, this is about how liquids and gases move around about. What's that got to do with the channel tunnel? Well, if you think about a train going through a tunnel, if you've ever been to the Glasgow Underground or been down in London in the tube, there are 3 ways that you know a train's coming. One is the little indicator board tells you a train's coming. The second is you can hear it. And the third is you can feel it because the wind starts to come out the tunnel because the train is pushing a big lump of air ahead of it. Now in underground systems that's fine because you've got a station every 3 or 4 miles, which means that air's got somewhere to go, it's got somewhere to vent to. But if you think about the Channel Tunnel, it's got about 35 kilometres from one end to the other, and that air has got nowhere to go. And what would happen if we couldn't get rid of that air is it would build up and it would make it more and more difficult for the train to pass through the tunnel. So the engineers had to look at computational flow dynamics and think about how do we get rid of that air. And what the air looks like in front of the train, we can see simulations here depending on which type of train it is. If it's one of the freight trains which are bigger, then we can see from this simulation that the turbulence and the amount of air which builds up is greater for a freight train than it is for one of the passenger trains. So it's quite a big problem for them to solve. So what did they do? Well, they came up with this idea of the piston relief duct, and you can see that as a kind of curved pipe which goes from one main tunnel to the other. And what that allows to happen is that large lump of air which is pushed along by the train going in one direction is then passed over into the empty tunnel on the other side, and it can then vent off in that side. So it prevents the train having to push that lump of air from one side of a tunnel to the other. And there are lots of these piston relief ducts all the way along. And that would be something which would be specified and designed using computational flow dynamics. The other thing they had to consider was that lump of air when it's being pushed along actually heats up because of friction. And one of the additional systems they've got in the tunnel is a cooling system which takes hot air away and cools it using cooling water. Once again, computational flow dynamics allowed that to be designed. This central tunnel, as well as being for maintenance, is also for evacuation of passengers in the event of a fire. And how that's achieved is that they make sure that the pressure in that central tunnel, the air pressure, is slightly higher than the pressure in the train tunnels. And what that means is, if there's fire and smoke in one of the train tunnels, because the central tunnel is at higher pressure, the smoke and the heat doesn't go in there, and it means that the passengers have got a place of safety. Once again, computational flow dynamics are what allowed that central tunnel to be designed properly. And it's actually had to be used for evacuation purposes. There's been 2 fires in the tunnel, one in 1996 and one in 2008. And because of the well-designed computational flow dynamics involved in building the tunnel, the passengers were able to go to that central safety and service tunnel and there were no fatalities. You can see the aftermath to the tunnel itself. You can see what happened to the concrete liners and the train and the carriages. But because of proper simulations done before the tunnel was ever constructed, this computational flow dynamics and finite element analysis has allowed the tunnel to be incredibly safe. I hope that's given you a very simple insight into how simulations are used when designing structures. Once again, if you've been looking for something much more in-depth and more complex, then this was not the video for you. So if you've wasted 8.5 minutes of your time, I apologise. Thank you for watching.